Hello. So when you're doing sample size, the first thing you need to know is how to find the z-value. Now these ones are main values. Well, 82 is not, and I noticed there are a couple on the homework where you need to find it. So when you're looking for the confidence interval, that's under distribution. So we hit second in distribution, and you go down to inverse norm. It's the third one. Okay. So it's the third one, and you hit enter. Now you need alpha over 2. So if we look at the, we'll start with a 90. If we look at a 90% confidence interval, the alpha, put a parenthesis, is 1 minus 0.9, because 90% would be 0.9. Close your parenthesis, but that would be alpha. We want alpha over 2, so we divide by 2 and close our parenthesis. So the 1 minus 0.9 is alpha divided by 2. And you hit enter. It gives your value. Now this is giving on the left side of the mean, but for the z-values, we want the positive. So that's why we're dropping the negative. And it's 1.645. If we find the 82, do the same thing. Second, distribute. Go down to inverse norm. Now this time it would be 1 minus 0.82. Close your parenthesis and divide by 2. And you get 1.341. So if it's not one of the usual ones, you can find it using your calculator. Now I rounded these to the 3 decimal places. Depending on the problems, they may want it rounded more. But as long as your values are close, I will go through and check and give you credit for them. And I'll show you what I mean, because these will be a little off. So if we look at the first one, when you're finding minimum sample size, use this formula. So we have to find z alpha over 2. So we look at the first problem, the confidence level is 99%. Well, 99% is 2.575. So we go 2.575, because that's our z. Let me put in parentheses. 2.575 times the standard deviation. In this problem, standard deviation right here, 67.2, divided by the error. We want it to be within 2.5. Either way, 2.5. So you put 2.5, and then you square it, which is right here. And then hit enter. Now you always round up, no matter what the decimal is, so it should be 4791. Now this I went 3 decimal places. If I would have went further, it would be more accurate. This is going to be a little bit off. So if instead I went second distribute down to my inverse norm, 1 minus, this was 99, so 0.99, close parenthesis, divide by 2. If I found my value and took a bigger decimal, 2.575829303. So instead of just using the rounding, if I use the whole thing, notice this will get closer. Instead of 4791, it will be closer to the 4794. Times 67.2 divided by 2.5. Close parenthesis and square it. See? 4794. So they want you to use the whole decimal, but only use, well, you could leave the negative because you're squaring it anyways. Let's try another one. So if you're using this estimate, your values are going to come off. They'll be off. If I look at the next one, it says, you want to obtain a sample to estimate how much parents spend on their kid's birthday. Standard deviation, 49.1. We want a 99% confidence interval, and it's within $1.5. Notice it's 99%, and that's what I have here. When your values, what you're doing is the same, you can hit second and enter, and it brings it back up. So we want this whole decimal because that's the 99% confidence interval. The standard deviation now is 49.1. So you could go up and change this to 49.1. Because that's what they have right here. And then the 2.5 we change to a 1.5. That way then I don't have to type this whole decimal in again. I just need to change that to a 1 and hit enter. Remember, we're going to round up, so it'll be 7110. 7110. Try one more. So this one is a 98% confidence. So second distribution, inverse norm. We want a parenthesis, 1 minus 0.98, because it wants 98. Close the parenthesis. That is alpha. We want alpha over 2. So divide by 2. So that's our decimal. And we want to multiply that by the standard deviation. Notice I just hit times and it took the whole answer. Standard deviation, 65.8, divided by the error, which is 2, and hit enter. Now I didn't square this yet because I didn't put the parenthesis. So then we can square it. $58.58. Always round up no matter what the decimal is. Try this with your statistics calculator. If you increase the confidence level, the sample size decreases or increases, okay? Well, we had a 2.326. If we increase the confidence level, so if we had 98, if we go to 99, how does that change it? So instead of this decimal, we're going to use this one. And since we don't need an exact value, we can use the rounded part. So 2.575 times the standard deviation, which was 65.8, divided by the error was 2, squared. Notice from 58 it went up. So it will increase. And this one's saying if you increase the error of the sample size. So we would take this 2.326347877 times the standard deviation, 65.8, divided by, if we increase the error, our error was 2, so we could increase it to 5 and then square it. Notice if we increase the error that we're allowing, then this will decrease because we're allowing for more error. If we allow more error, we can have a smaller sample size. But if you want to be more accurate, you need to have a larger sample size. Do one more. An engineer wishes to determine the width of a particular electronic component. If she knows that the standard deviation is 3.7, and how many of these components should be considered to be a 90% sure, so 90% confidence interval, and we're going to within plus or minus 0.2. So 0.2 is your error, or your E. So we need to clear this. We're going to, we could use this estimate, but then it will be a little bit off. So we're going to go second distribution down to inverse norm. Put a parenthesis, and you want 1 minus 0.9 because that's your confidence interval. That gives us alpha, close your parenthesis, and divide by 2. So then you have alpha over 2. Notice 1.645. But we're going to keep that whole decimal, so I'm going to put the answer in there. And then we multiply by the standard deviation, which was 3.7, times 3.7 divided by 0.2, because that's our error. And then squared. So we have 925, and rounding it'll go to 926. That's how you would do your sample sizes.